Friends, very good morning to everyone. We were dealing with retrosynthesis. We know that it is a strategy to synthesize the target molecule, in which we break up the molecule into smaller fragments, which we call it as synthons, and then join them to get the target molecule. Conceptual cleavage of the target molecule to get the possible starting materials is the retrosynthesis. While doing the retrosynthesis, we should have the good concepts of organic chemistry, starting from the types of reactions, mechanism of reactions. Also, we should have the knowledge about the workup of the reactions. And in the process, the order of events plays a very important role. Which reaction should be carried out first and which should be carried out next, and so on and so forth. It's very much necessary because of the fact that one group present in the molecule will influence the reactivity and also the orientation of the another incoming group. That's why we have to select the order of events in a proper way. Which should be first, which should be next, and which should be followed one after the other. To know the order of events, guidelines have been given. Today's subject of discussion is the guidelines for order of events. There are 9 guidelines given. These are not the rules but just the guidelines where we can follow wherever required and wherever not required we can change. Whenever required we can also change. The guideline 1 says while carrying out the reaction, the retrosynthesis, the analysis, we have to examine the relationship between the groups present in the target molecule. And we should look for those groups which directs the other incoming group to the right position. Here, if I take para-isopropyl acetophenone, I can split the molecules in two different ways. If I split the molecule at the isopropyl junction, I can get one of the synthons as isopropyl group, another synthon as acetophenone group. The two reagents we use here is acetophenone and isopropyl bromide. Or I can split the molecule at the acetyl junction and I will get corresponding acetyl chloride and isopropyl benzene, nothing but cumene. Which one is the right one? Here I have mentioned here, the first one is the wrong orientation, the second one is the right orientation. Let us look here, why is it so? In acetophenone, it has acetyl group, the carbonyl group, which is electron withdrawing in nature. As it is electron withdrawing, it withdraws the electrons from the benzene ring system. Thus, it reduces the reactivity. That's why reaction will be difficult. More than that, when it is electron withdrawing, it will be meta-directing. The incoming group, that isopropyl bromide, when I carry out Friedel-Crafts alkylation, the incoming group won't come at the para position, it will sit at the meta position. That's why I cannot take acetophenone and treat with isopropyl bromide to arrive at para-isopropyl acetophenone. In other words, if I take isopropyl benzene and treat with acetyl chloride, The isopropyl group, as it is electron donating in nature, it increases the reactivity of the benzene and it will be ortho para directing. That's why thus the ortho position there will be a steric hindrance and it preferably sits at the para position. That's why I'll get corresponding para isopropyl acetophenone. The order of event should be such that I have to break over the acetyl position and take isopropyl benzene and treat with acetyl chloride. Whenever there is an electron withdrawing group, what we should do? The guideline 2 says about this. Whenever there is possibility, disconnect the most electron withdrawing group at the first stage and add at the last stage. Why is it to be done? Because electron withdrawing group withdraws the electron and decreases the reactivity, and reaction will be very difficult to conduct, or more stringent reaction conditions should be used. That's why first we will disconnect electron withdrawing group and then we will add at the last so that the reaction will go very smoothly. If I take this molecule as an example, here it has methyl and the O methoxy group and two nitro groups and tertiary butyl group attached to the benzene. The electron withdrawing group present here is nitro. First I will disconnect that CN bond disconnection I have seen. I will get corresponding nitronium ion. The synthon nitronium ion can be obtained from the reagent nitric acid and sulfuric acid. Then I'll cut over here. The carbon carbon bond breaks. This becomes the tertiary butyl group, tertiary butyl cation, and the methyl derivative of paracrysol. Here, the tertiary butyl carbocation we can get from tertiary butyl chloride. And when I treat this molecule with tertiary butyl chloride in the presence of AlCl3, it undergo Friedel-Crafts alkylation and give the molecule whatever required. Then I will cleave the oxygen and methyl group. OMe I cannot directly attach to benzene. Methoxy O minus is electron rich. It is a nucleophile. Phenyl group, as we know, it is electron rich. Unlike poles attract each other, and like poles repel each other. As methoxy is nucleophile, which is electron rich, and benzene is electron rich, both repel. That's why we cannot add. That's why we have to cut over this oxygen and add methyl to the oxygen. CO bond I will break. I will get corresponding metacrysol and Me plus. Me plus we can obtain from dimethyl sulfate. I can take metacrysol, treat with dimethyl sulfate in the presence of the base like sodium hydroxide. O-methylation occurs to give corresponding O-methyl derivative. Then I'll carry out Friedel-Crafts alkylation with tertiary butyl chloride in the presence of AlCl3 and I'll get corresponding ortho substituted derivative. At last, I will add nitric acid and sulfuric acid. First, I have disconnected, and at the last step, nitro group, the electron withdrawing group has been added. Now we can appreciate the order of events to be followed for the smooth completion of the reaction. Guideline 3 says if fragment or functional group interconversion required, we have to do it. In this example, there is trichloromethyl group. Trichloromethyl group I cannot directly attach. That's why what I have to do, this trichloromethyl group, I replace it by another functional group, methyl. This methylated chlorobenzene I will take and treat with chlorine and phosphorus pentachloride or phosphorus. The methyl hydrogens gets replaced by chlorine. I will break over this CCl bond which I mentioned here. I'll get toluene group and Cl plus. I'll take toluene for this toluene synthon and I carry out halogenation with treating with chlorine in the presence of a Lewis acid. I'll get corresponding parachlorotoluene. Then I treat with chlorine and PCl5. The hydrogens in the methyl group gets replaced by chloro. Generally, in retrosynthesis or any organic compound, electrophilic substitution plays a very important role. We can add n number of substitutions, starting from nitronium ion to sulfonium ions to halogen ions and whatnot. And this reaction, electrophilic substitution, can be hastened up in the presence of an electron donating group like amino group. Always it is advisable to carry out electrophilic substitution in the presence of an amino group such that it activates the ring system and also it is strongly orthopara directing. This is the guideline 4 given. I take this molecule to be synthesized orthochlorobiphenylic acid. Carboxylic acid group directly I cannot introduce as carbon dioxide is a weak electrophile. I'll do fragment group interconversion. I'll replace this by Cn. Cn also Cn minus and benzene is also electron rich. I cannot add directly the nucleophile over here. That's why what I have to do, I have to again do fragment group interconversion or functional group interconversion. Instead of Cn, I will introduce NH2. This NH2, I will treat with diazonium. I'll convert into diazonium salt by treating with sodium nitrite and HCl. And then I'll get N triple bond N. N triple bond N can be replaced by treating with cuprous cyanide. I'll break CCl bond over here. Again, fragment group interconversion. Amino group directly I cannot introduce. That's why I'll add nitro group. Then if I reduce nitro group, I'll get amino group. I break Cn, I get biphenyl. Biphenyl I'll take as the starting material. I'll nitrate it with using nitric acid and sulfuric acid. I'll get corresponding nitro derivative. Then I'll reduce it to give amino group. Then treat with chlorine and AlCl3. It will be orthopara directing and the ortho position the chlorine group attached as already para position is blocked by phenyl. Hence, after that, I'll do diazotization. It becomes N triple bond N. Then treat with cuprous cyanide. I'll carry out Sandmeyer's reaction to give cyano. I will hydrolyze this in the presence of concentrated sulfuric acid to give carboxylic acid. In the presence of the amino group, I added chlorine so that it gives the incoming group directed towards the right position required. Further, guideline 5 says I have two orthopara directing groups in a molecule and they are meta to each other. When an orthopara directing group is there, already present, another group if I want to attach, it will attach either at ortho or para position. But if I wanted it at meta position, then what should I do? In that case, I will do it by adding a dummy amino group. The amino group in the presence of orthopara directing group attaches at para position and this amino group which is added I make it to undergo diazotization to give diazonium salt and this diazonium salt will be replaced later on by reduction. For example, I can explain this by taking the retrosynthesis of propoxychine, a local anesthetic. This is the structure of propoxychine. Here, I'll break the side chain. This side chain I can add to this parent molecule. CO bond breakage has occurred. I can take corresponding amino salicylic acid. Right. Here I can break open this amino group. Amino group is orthopara-directing, OH is orthopara-directing, and both are meta to each other. In that case, how should I do it? I'll break over here CN. Right. I'll get salicylic acid. I can take salicylic acid as a starting material, and if I here if I treat with I do nitration, the nitro group will attach at the para position over here. This is COOH meta directing. The meta position is this one, and OH is ortho para directing. Ortho is already black. That's a para group. Para position is this. That's why the incoming nitro group will attach at the para position. But I want this at the meta position. There is regio control problem. Hence way, what I will do, I'll take salicylic acid. It is OH is orthopara directing, COH is meta directing, both direct towards this fourth position. 1, 2, 3, and 4. Now, I treat with concentrated nitric acid and sulfuric acid, it generates nitronium ion. That nitronium substitute the hydrogen present at the fourth position by nitro. Then I reduce this by using hydrogen palladium. Nitro group gets reduced to amino. That amino is strongly electron donating group, and that's why I make it less electron donating by treating with acetic anhydride. I'll get corresponding acylamine derivative. This is a moderately activating and moderately orthopara directing. Now, the ortho to this NHAC is this position, and para position is already occupied by OH. In the presence of this NHAC, I'll carry out nitration. The nitration occur at the ortho position to the NHAC. Then I will hydrolyze this. Acetyl group goes away, giving amino. The amino I'll treat with sodium nitrate and HCl, and it gets converted into diazonium salt, which I'll replace by H3PO2 titrating. This diazonium salt will go away and H plus gets replaced. Now the nitro group I have attached in the presence of this amino group. Amino group which I have added and I have removed it. I am using it as a dummy. I reduce this, I will get corresponding nitro group reduced to amino, and I treat with the corresponding diamino, diethyl amino ethanol. I'll get the target molecule, that is propoxychine. We introduce a temporary group at the para position to the OH and then remove it after adding the amino group at the right position. This is how we accomplish the attachment of two orthopara directing groups meta to each other. Another guideline 6 says that there are few substituents that are very difficult to add. In that case, do not disconnect them. In case of guideline 4, we have seen we have used biphenyl directly. We have not synthesized biphenyl. We have not added phenyl to phenyl. In guideline 2, we have seen we use cresol and methylate it using dimethyl sulfate and sodium hydroxide. We didn't added OMe group to the benzene ring system. The guideline 7 is the extension of guideline 6. There are many starting materials which are available in the market. When they are available in the market, do not try to synthesize them in our laboratory. Purchase it and use it, like salicylic acid, anthracinic acid, phthalic anhydride, orthometa and paracresols, biphenyls, etc. Whenever there is unwanted reaction occurs in presence of certain substituents, then avoid that. For example, if I do nitration of benzaldehyde, I will get only 50% yield of metanitrobenzaldehyde. Aldehyde group carbonyl, it is electron withdrawing. As it is electron withdrawing, it pulls the electrons from the phenyl ring, making electron deficient, and it will be meta directing. I will get metanitrobenzaldehyde only in 50% yield. What is the another 50%? Is benzoic acid. Why is it so? Nitric acid, which we use for nitration of benzaldehyde, is also an oxidizing agent. It oxidizes the benzaldehyde to benzoic acid, and we get benzoic acid as a byproduct along with metanitrobenzaldehyde. In that case, we should not do this thing. We have to avoid this kind of reaction where we get the byproduct. We have to change our reaction route. The last guideline says that whenever there is orthopara isomers possible, there are isomers some of the times or many of the times it may not be separable because their boiling points will be very close to each other. In that case, what we have to do? We have to block the one position such that that part is not reacted at all. I'll explain this by taking the example of this following molecule. Here I can split this molecule. I can remove nitro CN bond breakage. I'll get corresponding phenolic derivative. I'll break over here. I'll get phenol. Or I can break first over here. Then I can break nitro. Here, this is root A, this is root B. If I take follow root A, first I will take this and nitrate it. It gives para derivative. I want at meta position. That's why root A is not possible. Root B is better. Phenol I will take, treat with nitric acid, you get 2,4-dinitrophenol, then nitro electron withdrawing group and meta directing. The meta position is adjacent to the OH group over here, and here also the same, do Friedel-Crafts alkylation. By following these guidelines, we can choose the order of events and achieve the target molecule synthesis. And there are n number of other things which we follow in the retrosynthesis, and those will be the subject of discussion in the coming presentation. Till then, have a nice day. Thank you.